Okay, it looks like people are still joining, so I'll give it just a minute or two, and then we'll get started. Okay, just check that everyone can see the slides and can hear me.
So yes, that helps.
Okay, thank you. All right, in that case, we should get started. Welcome, everybody. This is the IRTF Open Meeting. My name is Colin Perkins from the University of Glasgow. I'm the IRTF Chair. And welcome to the IRTF sessions at IETF 111. So to start with, the usual set of reminders, we have the note well, the intellectual property, a reminder that by participating in the IRTF, you agree to follow the IRTF processes and policies, and in particular, you agree to disclose any IPR that you're aware of following the terms that are linked from this slide. So this is the usual IETF intellectual property disclosure rules. In addition to that, the IRTF routinely makes available recordings of these online meetings, including audio, video, and photographs, and we record and publish those recordings online. We're being streamed in Meetecho, and we're also, I believe, going out live on YouTube for this session. If you unmute your microphone, unmute your video, and participate in this session, then you consent to appear in such recordings. And I'll also remind you that the chat is being recorded, and the chat logs are available on the IETF website after the sessions. In addition to that, we have a code of conduct, we have a privacy policy, and so on. If you release any personal information to the IRTF, it will be handled in accordance with the IETF's privacy policy. And by participating, you agree to work respectfully with the other participants. And if you have any concerns about that, the IETF Ombuds team can hopefully help you out there. We have a code of conduct and a set of anti-harassment procedures for the IETF, and those also apply to the IRTF sessions. So, what is the IRTF? The IRTF is the research arm of the IETF. It focuses on longer-term research issues relating to the internet, while the IETF focuses on shorter-term issues relating to engineering and standards making. The IRTF is a research organization. It's not a standards development organization. And if you're not familiar with the way the IRTF works, there's an IRTF primer for IETF participants that Spencer wrote in RFC 7418, which gives a good introduction to how the IRTF works. If you want to stay informed about what we're doing, we have a website, we have the usual social media, we have a reasonably active Twitter account, and much less active Facebook account, and I believe also a LinkedIn account. We've also got a low volume announcement list if you want to know what the IRTF is doing, and there's a general discussion list in addition to the research group lists. The main activities of the IRTF are organized as a set of research groups. The current set of research groups is listed on the slide. Of these groups, the Privacy Enhancements and Assessments Research Group met in the previous session. The rest of the groups, which are highlighted in dark blue on this slide, a meeting later in this week, so do look out for those, and do join the sessions if you're interested in any of those topics. The IRTF can publish RFCs. We don't publish standards track RFCs, but we can publish informational and experimental RFCs. We've had 2 RFCs published since the last meeting. The privacy enhancements, the PAF-aware networking research group published the PAF-aware networking obstacles to deployment RFC, which is a nice summary of some of the issues with trying to deploy PAF-aware networking technologies over the years, and trying to learn some lessons from those experiences. Dave Aran in the information-centric networking research group had an RFC looking at considerations on the deployment of quality of service architectures for CCNX-like information-centric networking protocols. In addition to the research groups, there's 2 other activities which we do. The first of these is the Applied Networking Research Prize, which will be the main focus of this session today. The prize is awarded to recognize the best results, the best recent results in applied networking. It's awarded to recognize interesting new research ideas of potential relevance to the Internet standards community, and to recognize upcoming people that are likely to have an impact on Internet standards and technologies. And we're trying to bring in people who would not otherwise get much exposure, would not otherwise participate in the IETF and the IRTF, and try and get a dialogue going between the research community and the IRTF community and the standards development community in the IETF. The website on the slide gives sort of details of this. The main focus of this meeting will be that we have 2 ANRP prize-winning talks to get today. Rudiger will talk about his work on network specification and verification, first of all, and then in the second half of the meeting, Sajjad will talk about low latency video streaming. We've got some really nice talks coming up on those topics. Again, thank you to the Internet Society, thank you to Comcast and to NBC Universal. We organized the prize in conjunction with the Internet Society, and we thank Comcast and NBC Universal for their sponsorship of the networking research prizes. In addition to the Applied Networking Research Prize, we also run the Applied Networking Research Workshop, and this is in conjunction with ACM SIGCOM, and that's running concurrently with the IETF this time, and the first of those sessions was in the previous slot over the last couple of hours. The Applied Networking Research Workshop is an academic workshop. It provides a forum for researchers, vendors, network operators, and the standards community to present and discuss emerging results in applied networking. As I say, this year's workshop is running concurrently with this IETF, and the program and all the papers and the recordings are on the website linked. And I'd like to thank Andra and Nick, who've been organizing the workshop this year, and thank you to Akamai and Comcast and ACM SIGCOM, who are the sponsors of the workshop. So that's about all I have to say. What we have for the remainder of this session is the 2 Applied Networking Research Prize talks, starting with Rudiger Berkner, who'll be talking about config to spec, and then following on with Sajjad Fouadi, who'll be talking about Salsify. Before we get to that, though, I believe Matt Ford from the Internet Society wants to say a few words to the prize winners.
Thanks very much, Colin. I'll keep this brief because I'm sure everybody's here to listen to the award-winning talks. It's a great honor and privilege for the Internet Society to work with the IRTF to deliver the Applied Networking Research Prize. As Colin mentioned, there's sort of two purposes to this program, really, to get exciting new applied networking research in front of the IRTF and IETF community, and also to introduce new upcoming researchers to the community as well. And if that sounds like something that you and your day job company would like to support, we very much welcome additional sponsors for this effort. The only other thing I have to say is that I'll be trying to take notes in the CodeMD. So if you do speak at the microphone, you might want to check that to make sure I've captured your name and your comment correctly. Thanks very much.
Okay, thank you, Matt. Congratulations again to the two presenters. We'll have the first video now, if Miteko can play the video, which is by Rüdiger Birkner. Rüdiger is a final year PhD student at ETH Zurich, advised by Laurent van Bever and Martin Veshev, and his work is centered around developing methods to improve network understanding and help the adoption of new network analysis and synthesis tools. If you have questions, we've got a couple of minutes after the talk, or put them into the chat, and I'll encourage Rüdiger to join the chat as well. Okay, thanks. If we can play the talk.
Hi everyone, my name is Rüdiger Birkner, and today I'm going to talk about config2spec, a tool to facilitate intent-based networking, or at least a tool to take some steps towards it. For quite some years, intent-based networking, or short IBN, has been on everyone's mind. And the idea of it sounds great. You specify your intent, and the network just behaves accordingly. No more cumbersome configurations. You need the intent, and you're done. Unfortunately, we're not there yet. Actually, there's still quite some ground to be covered, but at least there's progress. All major vendors have somewhat intent-based networking product or solution, and also in academia, a lot of work has gone into it. For example, there are network configuration synthesis tools that allow operators to automatically produce network configurations according to their intent. And there are many configuration validation and verification tools that allow to check whether your configuration satisfies your intent or not. Some of these tools made it even and are commercially available now. So imagine you have just heard about these tools and you want to try them out for yourselves. For example, you're about to deploy some configuration change and you want to make sure that the change really only does what you intended to do and doesn't break anything. So you start looking around and you find that today several network validation and verification tools are available. You check them out and you realize that they more or less all follow the same recipe. First of all, you get the config, you apply your changes, and you provide it to the tool. Second, you need to specify your intent. Third, you need to run the tool, you wait for the results. And finally, you check the results, and maybe you need to adapt something in your configurations, or you're good to go. So it's quite a straightforward process, no? But hold on, most of these steps are clear. Get the configurations, run the tool, act upon it. But what is actually this intent? What is a specification? Let's look at that a bit closer. So in general, a specification simply describes the behavior of a system. So as the name says, it specifies how the system should behave. Hence, in our case, in a network, a specification simply consists of all the policies that should hold in your network. So in this project, we consider policies from a policy language, and we support 4 predicates: reachability, isolation, waypointing, and load balancing. These are the most common policies in the network validation and verification literature. So for example, our specification could consist of the following policies for the given network. But what does it actually mean these policies should hold? The network can be in different states, routers and links can fail, and the network's behavior will change. For sure, the policies will all hold when all the links are up. But what if router R1 or some link fails? Or what if all the link fails? Do the policies still have to hold? So clearly, just having a set of policies is not enough. We also need a context under which these policies have to hold. So we can just extend our definition of the specification by not only requiring the set of policies, but also by requiring that the set of policies have to hold under a given failure model. Now, this failure model provides the missing context. An operator can specify all the concrete environments, so all the states of the network for which the policies should hold. So one concrete environment is basically one state of the network, where simply every link is assigned to be either up or down. For example, the operator could specify the following 5 environments, and in a realistic setting with a larger topology, specifying manually all these concrete environments is cumbersome and also not desired. So therefore, you can actually capture such a failure model in 2 parts, with a symbolic environment and a failure bound. The symbolic environment is basically the network topology in which every link is assigned one of 3 states, up, down, or symbolic. And symbolic simply means that the link can be either up or down. And the second part, the failure bound, simply provides a bound on the maximum number of links that can or are expected to be down at the same time. So together, this set of policies and the failure model make up the network specification. And this definition of the specification is actually widely used in today's network verification literature. So now that we know what the network specification is, we can come back to the recipe. And we should be all set to use the network validator to check our configuration change. Unfortunately, this is not the case. While the definition of a specification is actually quite simple, writing down a complete specification is actually extremely difficult. And this is not just in networking the case, but in general, as this tweet of a well-known researcher shows. The need for specification often prevents people from using verification tools. This is also what a paper from Hotnets 2019 by Ryan Beckett and Ratul Mahajan noted. So they basically said that outside of a handful of large cloud computing providers, the use of network verification tools is still sparse. And they even argued that the next frontier for network verification is to enable easy and effective use for the average network engineer. And actually, we also have our own anecdotal experience with that. A while ago, we were discussing with a network operator that mentioned to us that they were about to also try to deploy such a network verification tools. But in the end, the adoption of this tool fell through just because the tool required a specification. You might still wonder and ask yourself, is it really that hard to write down how you want your network to behave? Well, just take Internet 2 as an example. As part of this project, we analyzed the publicly available configuration from 2015 and found that its specification is made up of almost 4,000 policy predicates. Now imagine writing this specification by hand and doing this without mistake. Or if you are a network operator, would you know all the policies of your network? Or could you fully describe its behavior? I would really be curious to discuss this with you and hear what you have to say. But in any case, don't worry. This is exactly where config2spec enters the scenes and is here to assist network operators. So together with Dana from Technion, Martin and Laurent from ETH Zurich, we developed config2spec, a tool that automatically mines a network specification. So config2spec takes as input your network's configuration and the failure model. And it automatically finds your network specification, so all the policies that your network enforces. In the following, we will first consider 2 Strawman approaches that individually explore one dimension of the problem at a time. Then I show you how we combine these 2 approaches to leverage their individual strengths. And in the end, we'll talk about config2spec's performance. So how long it actually takes to compute such a specification. So let's get started with the strawman solutions. When you think back to the specification, you remember that we only want to have those policies from the space of all policies that hold for every single concrete environment in the failure model. So we kind of have two dimensions, or we have kind of two search spaces. One is the failure model, so all the concrete environments that it contains, and the other one are all the policies. So it's a space of all possible policy. Together in combination, this becomes untractable. However, we can look at the two in isolation. When we look at it from the perspective of the failure model, so when we look at all the concrete environments, we can make use of data plane analysis. And when we look at it from the perspective of the policies, we can make use of control plane verification. So what do I mean by that? Let's first look at data plane analysis. At a high level, we can break down the problem of finding the specification for a failure model and the configuration into finding the specification for each concrete environment within the failure model. And then we just combine the outputs. So we start with one concrete environment from the failure model, and together with the network configuration, we compute the forwarding state using data plane analysis. From the forwarding state, we can easily determine whether two nodes are reachable, isolated, and so on. So below here, I show you kind of an abstract illustration of this. The blue area represents the space of all possible policies. After running data plane analysis and finding all the policies for this one concrete environment, we can narrow it down, and we have kind of the set of policies that hold only for this one environment. So now we continue one environment after the other. And finally, at the end, we have the specification for each concrete environment in isolation. And since the specification of the full failure model is a set of policies that holds for all of them, we can simply take the intersection and we will end up with the network specification. So as you can see, by intersecting one by one, we start with a very rough over approximation of the specification and refine it step by step. And finally, we end up with the network specification. So when we now look at the problem from the perspective of the policies and we use control plane verification, we have again the same situation. We have a large number of candidate policies. We have the failure model and the configuration. And with modern verification tools, we can easily check if a single policy holds for the entire failure model or not. So from that space of all policies, we can select one policy, feed it together with the config and the failure model to the verifier, and the verifier will tell us whether this one policy holds for the failure model or not. Now we can do this for every single possible policy separately, verifying them one by one, and ultimately obtain the full specification by taking the union of this. So here we kind of under approximate the specification and increase it step by step until we reach the full specification. So to quickly recap, both techniques have their pros and cons. Data plane analysis can find all the policies that hold for a single concrete environment, whereas control plane verification can check whether one policy holds for the entire failure model. So the strength of data plane analysis is actually to quickly cut down the candidate space, as with checking one single concrete environment, one can already rule out a lot of policies. And control plane verification is very good at verifying a small set of candidate policies and quickly identifying which belong to the specifications and which don't. So the natural question, or actually I already led to this, is why don't you combine the two approaches? And this is exactly what we do. So internally, config to spec consists of multiple modules. First of all, of a data plane analysis module and the control plane verification module, and it consists of a predictor. And this predictor dynamically decides whether to use one or the other, always favoring faster completion. So let's look at this at the high level. In the beginning, we start with the set of all possible policies as our candidate set for the specification. And this I try to illustrate with the blue area behind me. We start with data plane analysis, pick one concrete environment, see what policies hold for this environment, and intersect that with the candidate set. We continue, pick another concrete environment, and so on. We quickly manage to reduce the candidate set by a lot. However, we continue with this until kind of not much more progress can be made. The size of the candidate set stabilizes. And at this point, the predictor decides to switch from data plane analysis to control plane verification and starts to pick one policy after the other and verify them. It will check whether these policies hold for the failure model, some won't, some will, and it continues one policy after another until we have checked them all and config to spec terminates and we have found the full specification. So to make config to spec really work, we optimized both approaches. Following, I will just present the intuition. First of all, we can speed up data plane analysis or kind of the process of narrowing down the candidate set a lot by choosing the right environments to analyze. We do that based on the remaining candidate set. So we always pick the next environment that maximally disrupts the forwarding state with respect to those policies. To speed up the verification, we can kind of do three things. First of all, we can group policies. So instead of checking them one by one, we check them in small groups. Second, we can consider dependencies. For example, if we check a reachability between 2 points and we see that it doesn't hold, we don't need to check a waypointing policy between those points, because we know if the reachability doesn't hold, waypointing can't hold either. And as a last part, we can trim policies without even verifying them. So we can trim policies which cannot hold because of topological constraints. Just think of a failure model that allows for 2 link failures. We have a topology that has 2 different paths between a given set of nodes. And we know that there can't be a reachability between those nodes under 2 link failures if there are only 2 paths. So there's no point in verifying this policy. We know beforehand that it doesn't hold. So now, finally, let's look at how config to spec performs. To this end, we have fully implemented config to spec in about 5,000 lines of Python and Java code, and we rely on 2 state-of-the-art tools, Batfish for data plane analysis and Minesweeper for control plane verification. To test config to spec, we have generated configurations using a tool called netcomplete, and we did this for 3 networks, a small, a medium, and a large one. Let's look at the runtime of config to spec. Let's look at how long it takes to actually find such a specification. Now, in the following, I will only show you the results for the largest topology, which has roughly 160 routers. For all the other topologies, the results were similar. Obviously, it was faster, but they were qualitatively similar. On the y-axis, we show the runtime in hours. We make a difference between the BGP and the OSPF configurations, because OSPF configs are much easier to deal with and hence faster. In addition, we split up the time that the config to spec used into the time it used for data plane analysis and the time it used for control plane verification. We ran the analysis for 3 different failure models for up to 1, 2, and 3 link failures. Now, there are 2 special cases to consider. The first special case are failure models consisting of few environments. Interestingly, we never use verification in cases where we only allow up to 1 link failure. And this is due to the fact that there are only very few concrete environments, but a lot of candidate policies. So the predictor decides that it is faster to just iterate through all of the environments instead of trying to verify the policies. On the other hand, the other special case are situations where we allow for a lot of link failures, because then the trimming is extremely efficient and there are actually not that many candidate policies left that we have to check. So it's faster to actually just go through the policies and check them one by one instead of going through all the environments. The worst case is somehow in between, where we have a lot of concrete environments to consider, and we also cannot discard many policies because of topological constraints. In that case, it took almost 14 hours for config to spec to find the specification. And as you can see, most of the time is spent verifying the policies. Obviously, if you have a larger topology, it will take longer. However, note that you don't run config to spec whenever you perform a configuration change. You run config to spec once or twice to learn the specification, and then you can use that specification for verification, synthesis, and so on. With that, we're already at the end of this talk. So I presented to you config to spec, a system that takes on the challenging task of automatically mining a specification from the configuration in the failure model. And after all this, you might think, great, we have the network specification, and now what? First of all, the learned specification is useful for verification, as explained in the beginning. However, it's also useful beyond verification. For example, one can use it for what-if analysis. So you can compute the specifications for different configurations and check what happens if you do this or that. Second, you can use it also for config streamlining, which means you learn the specification for an existing configuration, and then you want to synthesize a new configuration that has the same behavior, so the same spec, but uses a different mix of routing protocols or protocol features. And finally, config to spec can help you just better understand your network's behavior. So if I raised your interest, I really invite you to check out our NSTI 20 paper, as there are more details to config to spec than what I covered today. In addition, we're still working on config to spec, trying to improve it. So if you have any opinion on it, if you think this is useful, please let us know. So please reach out to us, either to my email address or visit our website. Thanks a lot for your attention, and I'm happy to take any questions.
Okay, thank you, Rüdiger. Can you all hear us? Yes. So, are there any questions for Rüdiger? I see Jonathan had something in the chat. Jonathan, do you want to bring that to the microphone? Or?
Sure. So I was just wondering if you said at the beginning of the talk that currently, you might have to write a 4,000 line spec and then verify it, and writing that spec is very hard. So if we assume that that 4,000 line spec is the intended one, then your tool will generate me a 4,000 line spec. But how do I know if that's the spec I wanted? I know it's the spec I have, but how do I know it's the one I want?
Yes, so this is a very good point. So, of course, we will not learn the intended spec, but the spec that your config implements. And then you say, well, 4,000 predicates, it's way too much. If I go through it, maybe I forget what was at the beginning, how it interacts. And this is really, I think, one thing that we're working on. So kind of what I hinted at the end, one of the things is that we can do anomaly detection on the specification. So if we see that all the routers can reach certain destinations, but one router cannot, then maybe this is anomaly, something that you didn't intend to do. And we will point this out. And into this anomaly detection goes also a bit of a second approach of summarizing your specification. So instead of the specification is very low level, it says router R1 can reach this prefix, router R1 can reach the next prefix. So instead of listing all those predicates one by one, you can kind of summarize them and say router R1 can reach the entire prefix space.
Okay, thank you. Are there any other questions for Rüdiger? So I had one. So the generated specifications, you said they were quite low level. Are they basically human readable, or are they too low level to be usefully editable? or usefully readable?
So I think that they're usefully readable, but for trained, it's so let's say like a network configuration, right? That it's quite low level, but if you're trained, you know what it's doing. Yes, exactly. It depends on the human. But it's also what current specification tools expect you to provide as an input. So I hope, yes, a human operator will be able to work with it.
Sure. Okay. Okay. Is it possible to then feed them into a synthesis tool and generate the configuration and complete the loop?
Yes, yes. So or this is one of the ideas, right? That what I pointed kind of hinted at the end. So maybe you want to switch to a different routing protocol, switch from OSPF to ISIS, and want to make sure that it behaves the same way. Obviously, you need to have a synthesis tool like NetComplete, for example, that is able to do that, but then you can feed in the specification. However, what is really kind of a challenge is the policy language or kind of the predicates that we support, because maybe we cannot cover all the behaviors that you want, or the certain the predicates that we have at the moment are kind of data plane policies, but maybe you have more control plane policies, like prefer the route from this neighbor over this neighbor, if we talk BGP, or don't provide transit for certain neighbor, and this is at the moment not supported in config to spec.
Sure. Okay. Hesham.
Which got acquired by VMware. And I think it does something similar. Verifies that the configuration is correct, or the behavior of the network conform to the specification. So maybe I should read your paper to find out what you have done differently or better or more, but I see some similarity.
Yes, yes, I invite you to take a look at it, and also just reach out to us with any feedback or any ideas, or yes.
Yeah, no problem. Thank you very much.
Okay, thank you. I'm conscious that we don't have too much time today, so I see there's one more question in the chat, so maybe you could answer in the chat. What
Yes,
we do.
we'll do that.
Thank you again. If you're around for the rest of the week, I would perhaps encourage you to have a look at the Network Management Research Group, which is, I guess, working on similar topics.
Yes,
So,
thank you.
Thank you. Yeah. Okay, and the next talk today is by Sajjad Fouladi, who's a PhD candidate in computer science at Stanford University, advised by Keith Winston. Sajjad is broadly interested in computer systems, focusing on distributed applications, massively burst parallel computing, and video. And today he'll be talking about Salsify, which is a low latency network video codec, which achieves low latency through tighter integration between the codec and the transport protocol. If we can play the next video.
Hello, everyone. My name is Sajjad Fouladi, and I'm a PhD student at Stanford University. Today, I'm very excited to tell you about Salsify, a new architecture that we built for real-time video systems. So real-time video is a category of internet video delivery systems. And in this setting, we have a sender that has a camera and it wants to transmit the video feed over the internet to a receiver. What makes real-time video special is its latency target. We want the video to be delivered as fast as possible. So if something happens at the sender side, we want to see the video of that at the receiver side almost immediately. And we care about this latency so much because usually there is an interaction going on in the opposite direction that relies on the timely delivery of that video from the sender to the receiver. One good example is called video gaming, where the game, instead of on the local machine, is actually running on a remote server, and the player sees a video stream of that video that is delivered over the internet. Another example is collaboration of robots,
or remote surgery, where the surgeon is relying on a video feed to do the surgery from a remote location. And of course, the most prominent application of real-time video system, video conferencing, something that has been a big part of our lives over the past year. So the problem that we tackled in SolSafe was how these systems react to variations in the network. So here I'm going to show you one example. We are doing a video call with this very nice guy at NASA using one of these real-time video systems, LibRTC. And here you can see the network throughput graph. That shaded region shows the network capacity, and the line shows the amount of data that the program tries to send over the network. In this scenario, the capacity is slowly going to go down. It reaches 0 for a second, and then it will go back up again. Let's see how WebRTC reacts. Let's look at the video again. The capacity is slowly going down, and it reaches 0, and the video freezes, understandably. But now the network is back, but it takes WebRTC several seconds to recover the video. So if you look at this part of the graph, you can see WebRTC actually tried to send more than the network can handle. Those packets are either going to be dropped or queued. Both will cause stalls and glitches. And then it had to spend several seconds to recover from the mistake that it made earlier. A 1 second outage here caused WebRTC to spend several seconds recovering the video. So in SolSafe, we explored a different design. In SolSafe, we are tightly integrating a transport protocol and a video codec that allows the system to respond quickly to the changes that happen in the network condition. Okay, before I get to SolSafe's architecture, let me tell you a little bit about the conventional design. So the current systems, they have two important components. One is a video codec responsible for compressing the video, and one is the transport protocol responsible for sending that video over the network. And these two components talk to each other through a very narrow interface. The transport protocol has some notion of the network capacity, like a target bitrate, and it communicates that information to the video codec occasionally, like every second or every 2 seconds. And the video codec adjusts its internal parameters, tries to target the bitrate that it received from the transport protocol by setting things like quality and frame rate. And it produces frames that the transport protocol has to send over the network to the receiver side. And there has been decades of research and development on these components. We have all these video codecs, that offer better and better compression ratios. And we have all these different transport protocols built for different targets and different types of networks. And every time that we want to go and build a better real-time video system, we go and improve these individual components. Let me give you one example. Like, researchers actually knew about this problem that I showed you in the beginning. They studied the Skype and saw that Skype, in face of network variability, doesn't really do well. Like here, Skype tried to send more data than the network can handle, similar to WebRTC, and it caused a very huge spike in delay. So they said, okay, it seems that Skype has a problem predicting the variable network capacity. So they built a better transport protocol that accurately can match these variable network capacity. Great. But unfortunately, just improving the network components didn't save the day, because we totally forgot about the video codec, and the video codec has a very big flaw. And that's the fact that the codec can only achieve that bit rate on average. Like here, we asked the VPX encoder to target 2 megabits per second, and it produced a video that on average is at 2 megabits per second. But then you look at the size of individual frames, they are all over the place. And even a frame like this that is over the network capacity can still cause packet loss and congestion in the network. So the problem is that we have a codec that can only respond to changes in the target bitrate over coarse time intervals. So even if we have a transport protocol that can have a very accurate estimate at any point in time, we don't have a codec that can respond to that high resolution prediction from the transport. So in Salsify, we explored a more tightly integrated design where the transport protocol and the video codec work together within the same control. So I'm going to start by telling you about the transport protocol in Salsify. The transport protocol in Salsify only answers to one question: what should be the size of the next frame? So there is no notion of average bitrate or network capacity here. The transport tells me if you want to hit your target latency, your next frame should not be over a certain size, like 10 kilobytes or 50 kilobytes, based on the network conditions. So now the codec, the video codec, might be able to use that information. But as I told you, the codec has trouble hitting a certain size for a single frame. It tends to overshoot or undershoot that target. The transport tells me the network can handle a frame of maximum 10 kilobytes right now, but the codec may produce a frame that is larger or smaller than 10 kilobytes. So what can we do here? One solution might be just doing trial and error. We encode a single frame at different quality levels and just pick the one that fits the network. Sounds like a good idea, but unfortunately with the current codecs, it doesn't work. So when you look at the video encoder, the program responsible for compressing the video, it receives frames and it produces the compressed bit stream. When we look inside that black box, it's actually stateful. So when you encode a frame, the encoder goes through a state transition. And that frame becomes a part of the video stream. And now it has to be sent over the network and it has to be received by the receiver because the future frames are going to be dependent on the state that is produced by that frame. And when we look at the interface that we get from the current video codecs, we see that there is no way to undo an encoded frame. The state is completely internal to this encode function, and there is no way to save or restore that state. So in Salsify, we built a functional video codec for the VP8 format that makes that state object explicit. Now, if you encode a frame and you don't like the results, like if it's too big, you can just discard that, go back to the previous state, and encode a new version. So using this, Salsify can explore different execution paths without committing to them. So for every frame in the video, Salsify produces a version with a slightly higher quality than the previous one with a slightly lower quality and thus smaller size. And it also gives the transport the option to discard the frame. If the transport doesn't like that frame, the codec can silently just go back to the previous state. So this is how these components come together in a single control. The transport has some estimate for what the network can handle right now. It says the network can handle 30 kilobytes. Great. And the codec gives transports two options, one with a slightly better quality, one with a slightly worse quality than the previous frame. And the transport picks the one that doesn't go above that estimate. And it tells the codec, this is the option that I picked. And the codec will base the next frame based on that exiting state. Now the transport repeats the same thing. And sometimes the situation is that none of the options fit the network. Like here, the target is 5 kilobytes, and the options are 70 kilobytes and 50 kilobytes. So the transport tells the codec, just discard those frames, and then base the next frame on that exiting state. So the frames are discarded, and now the codec moves on to the next frame, and the cycle continues. So as you can see, there is no notion of frame rate. We are not committed to sending like 30 or 40 or 60 frames per second. We only send the frames over the network when we know the network can handle them and they can be received in a timely manner at the receiver side. Okay, let's take a look at the results. And before I go any further, let me show you a comparison between Salsify and WebRTC in the video that I showed you in the beginning of this talk. So same situation for both. The capacity is going to go down and then go back up again. That's how Salsify reacts. So on the left side, you see Salsify. On the right side, you see WebRTC. So the network is out, and now it's back. And you see Salsify has quickly recovered. And if you look at the throughput graph in Salsify, you can see that it gracefully tries to match the network capacity, while WebRTC has trouble keeping up. In the second demo, I'm going to show you how Salsify reacts to occasional network outages. So at different points in time, the network is going to be out for 1 second. Let's see how WebRTC and Salsify react in this situation. Left side Salsify, right side WebRTC. The network is out. Salsify has recovered. And now WebRTC. Again, the network is out. Salsify has recovered. And now WebRTC. Network's out. Salsify has recovered. And again, it takes WebRTC several seconds to recover from that 1 second outage. And when we look at the network throughput graph, we see that WebRTC basically disregarded whatever was happening, in the network and just kept sending data at the old rate here. In order to evaluate Salsify, we built a measurement testbed that is capable of basically testing any real-time video system as a black box without requiring any modification to that. You can read all about this measurement testbed in our paper. Just one thing that I want to mention is that this measurement testbed uses a barcoded input video. Each frame in this input video has a unique barcode, and using this barcode, we can actually match frames at the sender and the receiver side, and we can see what was the change in the frame quality and how long did the frame take to reach from the sender side to the receiver side. So we are capable of measuring delay and quality on a per frame basis here. Using this measurement testbed, we compare Salsify performance to Skype, WebRTC, FaceTime, and Hangouts. Here on the y-axis, you can see the video quality, and on the x-axis, you can see video delay. So the x-axis is flipped, better is up and to the right. We wanted to see how the ideas that we had in Salsify actually contributed to the final results. So we started by implementing a real-time video system that works very similar to the conventional design, and it ended up kind of close to the other systems. Then in the conventional design, we went and just replaced the transport protocol with this video over transport protocol that tries to take control of the video on a per frame basis. We still have a conventional codec. It has to come up with the right parameters up front, but now the transport tries to set a size for each frame. As you can see, the delay was improved, but the quality, it actually dropped a little bit. But now, in the full version of Salsify, when we put together all these components, the video over transport protocol and the functional codec, that's when we can achieve better delay and better quality than the other systems. So these are the results on Verizon LTE trace. Here we have the results on AT&T LTE trace, where again, Salsify achieves better delay and better quality than other systems. And here we have the T-Mobile UMTS trace, which is a very troubled link. You can see delays up to 18 seconds. And again, Salsify achieves lower delay and higher quality compared to other systems. And of course, there are situations where Salsify doesn't really offer an advantage over other systems. One case is that when you have no variations in your network. Here, you can see the results when we ran Salsify on a network with constant capacity and very low rate of packet loss. Let's just take a step back and see what happens. So the individual components that we have in Salsify are not exactly new. Like the transport protocol is a very dumbed-down version of packet pair and a Sprout. The video format that we are using is like 13 years old. And the functional video codec that I told you about was built for a different purpose, and because it was built by one person in 3 months, its compression efficiency and speed is way lower than commercial codecs. What's new in Salsify is the architecture, the way that we put these components together that allows the system to jointly control the codec and the transport and respond faster to the variations in the network. We believe that in the context of real-time video systems, going and making better video codecs probably won't give us that much. But if we go and start making changes to the overall architecture of these video systems, we can still yield significant benefits. So Salsify is a new architecture for real-time internet video. It tightly integrates a video over transport protocol with a functional video codec, allowing the system to respond quickly to the changes in the network conditions. Salsify achieves lower delay and higher quality when compared to FaceTime, Hangouts, Skype, and WebRTC. Thank you.
Okay, thank you. Excellent talk there. Hi, are there any questions? I see Hesham is in the queue, and then Jana. Hesham, go ahead.
Presentation. Thank you very much. Have you looked at holographic communications?
No. No.
Do you plan to?
To be honest, that's the first time that I'm hearing the term. So I'm definitely going to look it up.
Holography. Yeah, holography.
Yeah, this is the first time I'm hearing the term, but I'm definitely going to take a look at it.
Okay. Thank you very much. We can talk offline.
Of course. Thank you.
Okay, Jana.
Hang on. Can you hear me?
Yes, we can hear you.
Wonderful. Thank you so much for that lovely talk, Sajjad. It was lovely to see Salsify presented here. I've known this work for a little while, and I'm curious to know if there's been more progress in this direction, either in terms of deployment, like in terms of people picking this up and trying to run with this, or in terms of your own work on because, as you said, it's really lovely. The architecture is fairly simple, but it's effective, and that's what you're demonstrating, in my opinion, here. Well, it's a lovely little piece of work that shows how far apart these two worlds of video codecs and transport are, unfortunately, despite so many years of work. And so I want to thank you for revealing that. But I'm curious to know if there's more work that's happened since the paper was published a couple of years ago.
Thank you so much for the question. I think the biggest hurdle around deploying Salsify in real life is that, before we didn't have support for these kind of encoding, this stateless codec, in hardware. And, if you can't have a video conferencing application on your phone, that you can't really expect something like that to be deployed. The good news is, I think like about a year ago, stateless codecs actually found their way into Linux kernel. And I think today you can go and actually buy chips that have stateless codecs that basically offer the same functionality that we had to implement from scratch in software. So in terms of, seeing more and more things like that, availability in the hardware, I think there is actually a path forward to bring architectures like Salsify to production. But until that happens, and we can actually have those kind of hardware in our phones, the big idea in Salsify, I don't think that we can actually get that to deploy widely. But one other thing is that there are many, I think, small details in Salsify that still can be implemented, even in this current form of these systems. Especially one thing that I briefly mentioned, the fact that Salsify can drop frames after the fact, the drop frames after they are encoded. So, in the past couple of years, I've spoken to people at WhatsApp, Google, all these companies, and there are these ideas that we are trying to communicate and, have them implement in their systems. And I think a lot of them are actually useful. But if you're talking about the overall architecture, I think we are still a few years behind until we have these kind of interfaces available widely in hardware.
I would encourage people in the room to go talk to Sajjad, just because there are people in this room from the same who worked on or who do work on the products that you mentioned. They're probably sitting around here. So yeah, I definitely encourage them to go talk to you. Thank you again for the talk. It was lovely.
Thank you. Thank you very much.
Thank you. Ali.
Yeah, thanks for the talk. I put my question in the chat window, but let me, since we are just talking here, let me just rephrase the question again. So what I feel like in terms of stateless encoding, what you're doing is mostly, all intra coding, and then in that case, obviously, a lot of things get really simplified, and but the quality overall will suffer very, very greatly, in my opinion. So. Looking at the results in the paper and then in your slides, I feel like, using the SSIM metric is not really the correct term here, because when FaceTime or, some other applications that you showed in your results, when they use a much better codec than VP8, I mean, it's really unreasonable to expect that their quality is going to be less. Unless they suffer really very significant and very long freezes. Now, I feel like what you are doing with VP8 is mostly intra-coding, all intra-coding, and that simplifies the frame level rate control, as I mentioned earlier. But that is going to be detrimental to your overall video quality when compared to other, more professional video codecs that use predictive coding as well. So I'm surely going to look in more detail in your tests and results and simulations, but I just wanted to point it out. It's not very fair to compare an all intercoding video codec with a predictive video coder directly. So I just wanted to make that comment. But if you have any follow-up comments on that, I will be glad to hear. Thank you.
Thank you. Thank you so much for the question. First of all, only the first frame in the video is intra-coded. In Salsify, all the other frames are intercoded. They're all motion compensation compressed. And
but then let me ask this very quickly. Like you showed an example where for example, the transport says the next frame size should be this, and then you obviously need to pick, quantization factor or whatever to satisfy that size requirement, right? That means you might be significantly reducing the bitrate for that frame. Now, any frame who is dependent on that frame will also be low quality, because the source, the frame that they are using as the source will be low quality. So in that case, all the subsequent frames will be also impacted, not just that single frame, right? So.
So when we change the qualities between frames, actually we do that relatively. So we basically copy the quantizer from the previous frame and just fiddle that a little bit. So if you look at like the output video, the difference between two subsequent frames is not really visible even to human eye, and the changes, the most important thing is that the situations that we actually go and drop a frame. So when you get in a situation when there is a sudden drop in the capacity and just decreasing the quality a little bit won't help you, that's the situation where you go and drop the frame. Because later, you have to pay a very expensive price if you cause packet loss or any sort of packet queuing. And as you mentioned, increasing the quality and bringing the quality back is going to be difficult again, because your quality has dropped.
Exactly.
Okay, thank you. I'm conscious that we're running a little bit over time here. I don't want to cut the discussion off. Maybe people could join the Gather Town afterwards and try and catch up there, perhaps, if there's more to discuss. But again, thank you. Really interesting talk. Thank you, Rudiger, again. Also, two really interesting talks. The talks are available on the IRTF website if you want to look at them. I hope both Sajjad and Rudiger will hang around for some of the rest of the sessions later this week. I know we have the audio-video transport working group in about 20 minutes. So if Sajjad is able to hang around, and he may find that interesting. Thank you, everyone. As I say, the talks are online, and it would be good if we could get some discussion going. So thank you, and congratulations once again to everybody.
Thank you. Thank you.
And that's all we have for this session. So look out for the rest of the IRTF sessions later in the week. And thank you, everybody, for your time.